Hi, good afternoon. Thanks for coming out to attend this session. So I guess I wanted to just talk to you for a few minutes here about 10 Gigabit Ethernet as a next-gen camera interface and the new FLIR Oryx 10 GigE camera. So the GigE Vision interface is really the dominant machine vision camera interface in the market right now. Since the arrival of this interface, its combination of cable length, speed, reliability, and low total system cost have proven very popular, and it's really taken over the lion's share of the machine vision market right now. But more demanding applications requiring higher frame rates, higher resolutions, higher bit depths, and some combination thereof are really pushing forward the need for a higher bandwidth interface. And so there's some kind of workarounds right now. There's these link aggregation or lag systems that kind of double up on cabling. They require special network cards that support teaming. There's a bit of fiddly configuration required, and it really is just kind of a workaround for the moment. And so we see 10 Gigabit Ethernet as being a way to build on the strengths of GigE with greatly increased bandwidth. So just to give you kind of a quick comparison as to where 10 Gigabit Ethernet sits relative to some of the other common machine vision interfaces in terms of cable length and bandwidth. At 10 GigE over here, and that really sits the maximum spec is 100 meters over a Cat6a copper cable. So that combination of that long maximum cable length with high bandwidth, so that's equal to the next gen USB 3.1 Gen 2, which is a meter maximum cable length. So it's faster than single channel co-express, and just a little bit slower than camera link, but provides much greater cable length, greater reliability. There's a packet resend feature in GigE which cable link does, or camera link doesn't have. So yeah, I feel it represents a really solid combination of that performance, reliability, and long maximum cable length. So what do we actually get with 10 gigabits of throughput? Well, compared to, I guess, a couple of the other common machine vision interfaces here, if we look at the kind of the latest generation of high-performance global shutter CMOS sensors from Sony, you can see that at their maximum frame rate and bit depth and resolution, there's way more data than GigE can handle, and a lot more than USB 3.1 Gen 1. So really, to enable those sensors to run at their full potential, you need an interface like 10 GigE. One of the other important things about 10 GigE is there's lots of room to grow here as well. So the next generation and the generation after that of these high performance CMOS sensors will be supported on the 10 GigE interface. So I guess there's a couple of flavors of 10 Gigabit Ethernet as well, and these really differ based on the physical layer, or the PHY. And what that PHY is it's the actual electrical and mechanical connection between devices. And so we've really the two main ones are the 10G base T and direct attach. So 10G base T uses the same RJ45 connector that I'm sure you guys have seen on your laptops and your home routers and your switches at work. That'll get you 100 meters of cable length over Cat6a cable, or up to about 40 meters on Cat5e. I went on Amazon the other day and looked for a 60-meter Cat6a cable, $45. If you don't want pre-made cables, you can buy it in bulk. You can field terminate it. You just buy a box of little shielded connectors and cut it to whatever length you need. It'll also auto-negotiate to slower speeds. So if you take a 10 GigE camera, plug it into a Gigabit Ethernet switch, it'll just automatically drop down to that slower speed. The direct attach FLIRs, they use a much larger connector where the transceiver is built into the cable. The cable length with copper cable is much shorter. It's only about 10 meters. There's optical options that are available that can push that out to well over 1 kilometer, but it's a lot more expensive. So in the same Amazon search, $70 for a 2-meter copper cable, or $145 for a 20-meter cable. And you know, if you're talking about going over that, it gets a lot more expensive. And these are all pre-assembled cables, so there's a lot less flexibility there. So really the trade-off between the two is with 10G-based-T, they're much lower cost. You still got really long cable lengths, field termination, and that auto negotiation. The direct attach, it is a bit more power efficient, a little lower power. Yeah, we kind of at FLIR decided that yeah, all the advantages of 10G-based-T really made that the most attractive machine vision interface going forward. And I think the industry as a whole has kind of agreed with us. The 10G-based-T implementation of 10 Gigabit Ethernet is by far the most widely deployed. It's a mature platform, and this has led to a really favorable consumer ecosystem. So there's a lot of manufacturers in this space. There's you know, a wide variety of products, and that's pushing the cost down and really favorable for consumers. So you can see the adoption of that 10G-based-T relative to the direct attach. It's really just taking off. With that continued growth and investment in the development of this technology, we're continuing to see increases in power efficiency as well. Every generation of those FLIRs that's come out has yielded significant increases in efficiency. And as we're getting ready to move from the 28 nanometer process down to the 14, we're expecting that trend to continue. And so that's it's quite an exciting time. Besides just speed, what else do we get from 10 Gigabit Ethernet? Well, one of the things is much more precise software triggering. The 10 GigE interface provides significantly lower latency compared to Gigabit Ethernet. So for an application like a closed hash driving, where you want to minimize that latency between the input to your camera and your display, this is an excellent choice. Another thing we also get is as part of being part of the Ethernet standard, the IEEE 1588 Precision Time Protocol. And this enables clock synchronization between 1588 enabled Ethernet devices down to around 5 microseconds. So you can use this protocol with no user oversight. You just plug it in and turn it on to generate a consistent time base across your system. Or you can use a grandmaster clock and synchronize it to a GPS atomic clock and synchronize that to a real-world time. When Gigabit Ethernet first came out, the GigE Vision protocol as a machine vision interface, one of the things that was a real concern to people was the CPU use during that packet reassembly. I guess as part of the Ethernet protocol, the packets don't necessarily arrive in the order that they're sent, so the computer has to kind of rearrange them, put them in the right order, put the image back together, and transfer that into memory. And that took a fair bit of CPU in the early days. However, since then, Moore's Law has kind of come to the rescue, and the modern PCs have so much power available that even a 12 megapixel camera running at 60 frames a second, 5.6 gigabits a second of data coming in, to actually reassemble those packets and get the images into memory, uses a little over 0.5% of Core i7's CPU power. So it's really kind of a non-concern there. 10 Gigabit Ethernet also enables a really simple upgrade path. The backward compatibility with existing GigE Vision hardware and software means you can take a 10 Gigabit Ethernet camera and plug it into any of those existing systems, and it'll just work. It'll just step down to whatever speed is needed. It also gives system designers a lot of flexibility to kind of mix and match the hardware. So if you have a 10 Gigabit switch, and you need one super high frame rate or high resolution camera and then a couple of lower ones, well, you can combine those GigE cameras with 10 GigE cameras all on one switch, and it just works seamlessly. There's also a newly adopted standard just in the last few months that's really been finalized, that the N-base-T standard, and this creates intermediate link speeds between of 2.5 and 5 gigabits a second, and using just standard Cat5e cables. So this kind of provides a nice stepping stone, as well as additional link speeds that can kind of be mixed and matched with the 10 GigE. I just take one quick second to compare it to 10 Gigabit Ethernet to USB 3.1 Gen 2. Because while they both have 10 gigabits a second of throughput, now that USB 3.1 Gen 2 has adopted the more efficient encoding than the older USB 3 and 3.1 Gen 1 that lost about 20% of its throughput in just the encoding overhead. So they might have the same transfer rate, but USB 3.1 Gen 2 is not really ready for the prime time yet. The maximum cable length, the spec for that is 1 meter, which in a lot of cases isn't that useful. The industry is also really yet to standardize on a connector. This is likely to be Type C, but until that really comes together, there's limited availability of really industry-ready equipment. On the other hand, 10 Gigabit Ethernet is widely used in network infrastructure. It's a mature platform. There's a robust ecosystem around it, and high flex, high temperature locking industrial cables and equipment are readily available. So now that we're all sold on the 10 Gigabit Ethernet interface, I'll just take a second to talk about the new FLIR Oryx camera. And this uses that interface. And so we've got a live demo at booth 827 if you want to come by and have a look afterwards. So the target for Oryx really is integrators looking to build the next generation of high-performance vision systems. So we offer a 4K resolution, 60 frames a second, 10-bit depth. We're featuring the latest global shutter Pregia sensors from Sony, excellent low light sensitivity, high dynamic range, about 2 electron read noise. We also really focused on kind of that flexible deployment, so using all of the flexibility advantages of 10 GigE, that cabling, that backward compatibility. So support a really easy transition. So using our Spinnaker SDK, which is a GennyCam feature set, it's kind of industry standard. So any other vision system development you've done, you can kind of carry that over to the Oryx. And also providing tools to allow users to automate more on board the camera. So advanced GPI controls, clock synchronization, that sort of thing. So the preliminary specifications for the first 3 models we're going to launch are all based around those Sony Pregia's global shutter sensors. So the 5 megapixel, 8.9, and 12.3. And these all use 3.45 micron pixel. And they're all built around the C-mount optics. So there's a wide variety of really high quality, high performance lenses that are more compact and lower cost than F or EF mount lenses. To maximize the flexibility for integrators, we've given Oryx a 12-pin high-density GPIO. We have opto-isolated inputs and outputs, non-opto-isolated inputs and outputs, serial I/O, auxiliary, strobe, trigger, and power supply that operates over a wide range of voltages. We also spent a lot of time on the thermal design of Oryx to make it really as robust as possible. So this is designed and tested to operate at 50 degrees C ambient with no heat sinking, no active cooling, no moving air, no lens, no camera mount, just sitting there. It'll run 24/7 continuously, and so really robust, sort of industry-ready solution. Some of the features that we're really excited about with Oryx as well, a lot of onboard processing to offload the color processing and debayering onto the camera, the FPGA, rather than the host. So we have a 5x5 debayering, color correction matrix, which is really cool. Kind of takes the whole idea of white balance a step further and uses the actual spectral response of the sensor and the frequency, the wavelength makeup of the light to really come up with a much more accurate representation of color. Gamma, lookup table, saturation, sharpness, kind of the standard things there. There's a really powerful sequencer that lets you automate ROI changes, gain, exposure, build your own super HDR images. Then on the triggering side, we use logic blocks, counters, and timers, so you can build your own custom trigger modes, do things like missed trigger detection on board the camera. And there's serial I/O, and again, the 1588 precision time protocol. We back all that up with our new Spinnaker SDK. It's a GenyCam 3 API library, really built for forward compatibility and interoperability. And what I mean by forward compatibility is one of the really cool things about Spinnaker and the GenyCam way of doing things is that as new features are added to cameras or the software, to take advantage of those features, you don't have to rewrite all your code. Really just recompile your app and you've got access to all those new features. So it's a really, really streamlined development process. We support a wide variety of languages, all the major third-party libraries from NI, Matrox, Cognex, Halcon. Windows, Linux, ARM platform coming soon. Our SpinView GUI for Windows gives you a really intuitive way of controlling the camera, getting up and running with it, and kind of understanding how features are interconnected. We use all the standard naming conventions. The features are all searchable, and they're also cross-referenced to the old IADC system. So if you're used to working with FireWire cameras, you can search for all the feature names you're familiar with, and they'll come up in the new GenyCam system. We also back that up with a rich library of example code, knowledge base articles, and technical application notes. So what's coming next for Oryx? Well, the first camera we're launching is the 12.3 megapixel, and that's we're showing that in our booth right now. We'll be following that up with a 5 megapixel, and then an 8.9. And I guess stay tuned, because new features that are coming may include power over Ethernet, 35 millimeter sensors, 50 plus megapixel or ultra high res sensors, and power zoom, power focus lenses. So thanks very much for your time. If anyone's got any questions, please let me know.